In this video we're going to have a first look at how we can model time series in a Bayesian way. So lots of data in economics has a time series dimension, like GDP over time, growth, inflation, unemployment. These are all series that tend to vary over time. And there are a number of ways in which we can model that in a Bayesian way. And in this video we're going to look at the Gaussian process. So the idea of a Gaussian process is that we draw values not just from a normal distribution, but from a multivariate normal distribution. Yeah, so if we have a time series, let's say over 20 periods, then we draw a string of 20 values out of the normal distribution. And we need to specify what the correlation between those values is. So to understand how the Gaussian process works in a Bayesian analysis, we first generate our own data. So by now you should be able to read how we generate our own data. Yeah, so we have an x variable, so we think of this as time. So there are a number of ways you can generate your x values. Here we use linspace, so we move between 0 and 6 times pi, and n specifies the number of draws that we get in between those values, and we've set here n equal to 100. Yeah, so we add some noise to the series that we generate, and we plot it. So here we have the plot of our data, and you can see there is an upward trend, but there is also some periodic or cyclical variation around that trend. So the first correlation that we're going to be looking at is an exponentiated quadratic kernel. So this is the equation describing that. So basically what we say is that if you have two time periods, so let's say in this time range t and t prime, then the correlation between these two up to a constant for the variance is basically given by this. Yeah, so it's e to the power minus the square of the difference between those two values, meaning that values that are closer together tend to be more closely correlated than values that are far apart. And how quickly this correlation decays is determined by this L term here. Yeah, so when we use this kernel, we need to specify a prior for the L term that we see over here. This is a fairly standard kernel that's used in Gaussian processes. The notebook for this lecture contains a link to the kernel cookbook, which you can find on the internet. So let's specify our model in this case. So it turns out that in order to use pymc3 here, we actually have to turn our x variable that we defined above when we're generating our data into a column variable, so which has n rows and one column. So remember, n here is the number of samples that we drew from x. So we need to reshape x to turn it into a column vector. Oops. And then we say with pm model s, and let's call this model time series kernel. Then we say that h here is gamma distributed with h, 3, 1.0. Then we specify our covariance, so that's pm.gp.covariance, and the one that we choose here is our exponentiated quadratic. Our x variable, so that's the first argument here, is one-dimensional. Yeah, because it's a vector of dimension 1. So there's a number of rows, but it's one-dimensional. And then ls, which is the term for this L variable here, is h. So we draw this from the prior distribution, the gamma distribution for h. The notebook contains a link to the pymc3 page describing the gamma distribution, just in case you're not familiar with it. Then we say that the Gaussian process is pm.gp.marginal with the covariance function given by C, which we specified in the line above. We specify our noise term, so we say sigma is half Cauchy. Sigma with parameter 1. And now what we're used to is that we would write observed is etc. And it's the implementation for the Gaussian process is slightly different. So we say here that ys is gp, and then we say we want to have the marginal likelihood of ys, where x is equal to x and y is equal to y. So this is the y that we defined above when we were generating our data. And the noise term is given by sigma. Yes, so now we can run this and we have an error. So let's see what went wrong with... Oh yeah, okay, so I forgot my brackets here. So with PM model, let's see whether it works now. Yep, it seems to have accepted this. Now there are a number of ways in which we can sample from this process. Oops, not sure what's happening here. So up till now we've been using Markov chain Monte Carlo, so MCMC as a sampler. That you can still use that here, but sometimes it takes a bit long to sample with that. So here we're going to use what's called the Utv Sampler. So we're going to say that with time series kernel, so we say that the inference here is going to be PM Utv. I'll explain in a second what that is. So we're going to approximate, so PM fit 20, let's say 20,000 iterations, and then we're going to PLT plot approx hist. So let's see whether we didn't make any mistakes here. It seems to be running fine, so I can, this will take a second, so I can take some time to explain what's going on. So the idea of the Utv sampler is that instead of sampling directly from the posterior distribution, like MCMC does, and which takes quite long, here we first approximate this posterior distribution with well-known distributions like the normal distribution. Yeah, so we try to fit the posterior distribution of our parameters with normal distributions. That's what's happening here. That's what the fit here does. So we're not sampling yet here. We're trying to fit given distributions to the posterior that we have. The 20,000 is the number of iterations which we can specify. We can specify how long this process should continue. And you can experiment a bit by this. So if you take a higher number of iterations, you in principle get a better fit. And then to check the fit that you have, we plot this history of the approximation. And what we want to see here is a kind of inverse J shape. So I'll show you in a second what that looks like. So it's still fitting here. And then once we have the fit, we can use this approx object to draw our samples from. So we're almost there now. And here we have the plot. So basically what you can see is this sort of inverse J, or a hockey stick like shape, which suggests that the approximation process has sort of converged. Yeah, so this is sort of the effect that you're looking for. So it can be high in the beginning, but then it should sort of converge to the horizontal axis.